So in the previous lectures, we have looked at how to transform stresses in 2 dimensions. And we also learned how to find out the principal stresses and the principal directions for 2D stress states. So in this class or in this lecture, what we are going to do is do the same problem, but using a slightly different approach. So essentially what we are going to do is we are going to decompose the problem of finding stresses, the principal stresses and principal direction, to essentially an eigenvalue problem. Okay, and this is a problem that you probably have learned in your linear algebra or some of your earlier math classes. Okay, so what are the objectives? So essentially what we are going to do is we are going to understand how the principal stresses and directions essentially are equivalent to the eigenvalues and eigenvectors of the stress matrix. Okay, and we will derive how this thing comes about. Okay. So before we do that, the first thing I want to kind of note is that the 2D stress transformation equations that we got for sigma x prime, sigma y prime, and tau x prime y prime essentially can be written in a matrix form in a much simpler manner. So if you think about this as your x and y axis, okay, and this is your x prime and y prime axis, and again I want you to remember that the theta is always defined as positive in the counterclockwise direction from x to x prime. So if theta goes the other way, so for example if x prime goes in this direction, that theta would be considered negative. Okay, so this is the positive direction of theta as I have written it here. Okay, so the main thing that you want to note is that this stress transformation from xy coordinate system to x prime y prime coordinate system can be accomplished using matrices. So if you think of sigma xy as the stress matrix in the xy plane, that is something that you know, then you can convert that to the stress matrix in the x prime y prime coordinate system, essentially using a transformation matrix T. So that is the transformation matrix T. So what is this transformation matrix? The transformation matrix T is nothing but this, okay, which is cosine theta, sine theta, minus sine theta, cosine theta. Okay, essentially if you think about it, this is the transformation matrix for coordinate transformation from the xy coordinate system to the x prime y prime coordinate system. Okay, so essentially you can write your sigma in the x prime y prime coordinate system as this equation here. Okay, so what does it actually mean is that if you know the angle theta between x prime and x, okay, you can form this transformation matrix T, then pre-multiply the sigma in the xy coordinate system using T, and then post-multiply that with the transpose of the coordinate of the transformation matrix. Okay, that is T prime. Okay, so if you want to write it out fully, then sigma x prime, tau x prime y prime, tau x prime y prime, sigma y prime is this matrix T times sigma in the xyz coordinate system or xy coordinate system here times T prime. Okay, so this is essentially a compact way of representing the equations that we derived for these 2D stress transformations. Okay, now why we are doing this is because once we know that we can write the stress transformation equations in this as a matrix equation, then you can use that information to pose this problem of finding the principal stresses and principal directions as an eigenvalue problem. Okay, and that's what we are going to see next. Okay, so to show that this finding this principal stress and principal directions is equivalent to finding the eigenvalues and eigenvectors of the stress matrix, we again start with something that is very simple. Okay, we look at the stress state at a point. Okay, this is the stress square or the stress cube. Okay, and the stresses on this stress cube are given. So it is sigma x, sigma y, and tau xy because we are looking at a 2D stress state. Okay. Now, what we are going to do is we are now going to define a plane. Okay, and this plane here, okay, which I'm going to mark here, that is one of the principal planes. We are going to assume that that is one of the principal planes. Okay, and if that is the principal plane, then the normal to the principal plane is this NP cap. Okay, that is one of the principal directions of the stress, and this normal essentially makes an angle theta p with respect to the x-axis. Okay, so that is something that we define. So again, this is something that we define. the theta p could be negative, it could be closer to 90, it doesn't matter. So it's just theta p is some angle of this normal to the principal plane with respect to the x-axis. Okay. Now once we define this plane, we are now going to isolate this wedge here. Okay, and then look at the force equilibrium for that particular wedge. Okay, so and that is exactly what I have done here. So if you look at this diagram here, okay, so that is what it looks like. So the area of this inclined face is delta A, okay, and then you can find out what are the areas of the two perpendicular faces. Those are going to be delta A sine theta p and delta A cosine theta p. Okay, now what I'm going to do is I'm going to define my axis x prime to be parallel to the NP cap. So essentially, in this case, my normal to the principal plane is what I define as my x prime axis, and the y prime axis is along the principal plane. Okay. So now we know all the areas and the directions with respect to this wedge. Okay. And now we can essentially write down or we can draw the free body diagram for this particular case. Okay. So for the free body diagram, what we do? We multiply the stresses that are acting on those particular faces and multiply those stresses by the areas of those faces. For example, so this is sigma x, so this is also a sigma x. Okay. So the force due to the sigma x is going to be sigma x times delta A times cosine theta p, because the area of that face is delta A cosine theta p. Okay. So you do that for every stress that is acting on this wedge. Okay. So you have two stresses acting on this face here, okay, and two stresses acting on this face here. Okay. So we write the stresses or the forces corresponding to those stresses. Okay. And now we make use of the fact that when it comes to a principal plane, the shear stress on that plane is 0. Okay, that is an important consideration, and that is why on this face here, okay, on this face here, you only have one stress, which is due to the principal stress sigma p multiplied by the area over which it acts, which is delta A. There is no shear stress on that particular plane. Okay, and that is only true because we have assumed that this inclined face of this wedge is a principal plane. Okay, and once we have now drawn the free body diagram, then we can look at the force equilibrium along the x and y direction for this particular wedge. And essentially using that, we can try to formulate this problem as an eigenvalue problem. Okay, so that's what we're going to do next. Okay, so I have just redrawn those free body diagrams again. Okay, and now using the fact that there is no shear stress on the principal plane and applying force equilibrium along the x and y axis, you can first look at the sum of forces in the x-axis, and that should equal 0 because the wedge has to be in equilibrium. And we are doing the exact same thing here as we have done for the stress transformation equations. We take the force, we take the stresses, okay, multiply it by the corresponding areas, and then take the component of that force along the x direction. So in this case, for example, if you look at this term here, sigma p times delta A is the force due to the stress sigma p, okay, that is the force, and then this is the component of that force along the x-axis. Okay, so you do that for every stress that has a component along the x-axis. Okay, so there's going to be a component of this force, there's going to be a component of that force. Okay, and if you do all those calculations, all those forces, and then add them up together, you essentially get an equation like this. Okay. Now, once you get an equation like that, I essentially am doing some rearrangement of the terms. Okay, and you will see why we are doing this later on. So what I have done is I have essentially grouped all the terms with cos theta p and grouped all the sine terms with sine theta p. Okay, so that's why I have written this as sigma x minus sigma p times cos theta p plus tau xy times sine theta p is equal to 0. Okay, and you do the exact same thing for the sum of forces along the y direction. And if you do that, you will get an equation like this. Okay, and then you again rearrange those terms so that you have the first term corresponding to theta, cos theta p, and the second term corresponding to sin theta p. So essentially you're just grouping all these cosine theta p and sin theta p terms together in both these equations. Okay? And the reason that we're doing this will become obvious when we go to the next slide. Okay? So now these equations 1 and 2 that I have written here, okay, those 1 and 2, you can actually take those equations and you can combine them. Okay, and you can combine them and then write them in a matrix form such that the matrix on the left looks like this. Okay, the first term is sigma x minus sigma p. The second term on the first row is tau xy. The second term on the first term on the second row is tau xy, and then the other diagonal term is sigma y minus sigma p. Okay, and that multiplied by this vector cos theta p sin theta p is equal to 0. Okay. If you take those two equations and then combine them, that is what you get. Okay. Now we can go a little bit further and then we can essentially decompose this equation into two terms. Sigma x tau xy sigma y times cos theta p sin theta p, which is essentially this term here. Okay. And then the second term is going to be just sigma p times cos theta p sin theta p is equal to 0. Okay. So now it starts to kind of make a little bit more sense. Now what I can do is I can take the second term to the right hand side, okay, and then I write this as this matrix times this vector. Okay, this is a vector because it has two components and we are operating in 2D, and this is also a vector, okay, but multiplied by a constant. Okay. Okay, so essentially if you look at the form of these equations, this particular equation here, let's call this equation number 3, right? Then essentially it's of the form Ax equal to lambda x, okay, where A is a 2 by 2 matrix, x is a two-dimensional vector, and lambda is a constant, and again x is is a two-dimensional vector. So this essentially has the same expression as a eigenvalue problem. Okay, so the only difference or only thing that we note here is that it's not a general eigenvalue problem, but that is an eigenvalue problem that is related to the stress matrix. So the matrix A is nothing but your stress tensor, okay, in 2 dimensions, okay, and your X is nothing but the principal direction NP cap, okay, which is again the reason that we have it as an NP cap is because it's a unit vector. So, and your lambda, okay, is nothing but your sigma p, which is your principal stress. So essentially, if you solve this problem Ax equal to lambda x, where A is the stress matrix and x is the eigenvector, then essentially the eigenvalue that you get is essentially your stress principal stress sigma p. Okay, and the main thing that you want to notice that the NP cap is essentially the vector that is perpendicular to the principal plane. Okay, so essentially now it becomes clear to you that solving for the principal stresses is essentially solving an eigenvalue problem. Okay, so few things to kind of think about. So one thing that is, that is obvious is that the eigenvalues of this matrix sigma, okay, are essentially the two principal stresses sigma p1 and sigma p2. Okay, again, we are now looking at only problems in 2 dimensions, so essentially we have only 2 principal stresses. Okay. We will subsequently, generalize this for the 3D case, maybe in a couple of lectures. Okay. The other thing that you want to notice that the corresponding eigenvectors to sigma 1, p1 and sigma p2 are essentially the principal directions. Okay. So these, when I say principal directions, what you must immediately think about is that these are the vectors that are perpendicular to the principal planes. Okay, so the principal directions are essentially the vectors that are perpendicular to the principal planes. Okay, and the other way you can also rewrite this equation number 3 here. Okay, equation number 3 here is that you can write it as A minus lambda I times x is equal to 0, just as I was written here. Okay, so the reason that we are writing this is because this actually helps you to solve the problem. So initially we showed that the eigenvalue problem and finding the principal stresses and principal directions are essentially the same. But now we are recasting the problem so that it makes it easier to solve it. Okay, so now this I matrix here is nothing but your identity matrix. It is 1, 0, 0, 1. Okay, so A minus lambda I times X equal to 0. Okay, I want you to note that A and I are two-dimensional matrices. X is a 2D vector, and this 0 vector here is again a 2D vector. Okay, so this set of equations here is actually two equations. Okay, two scalar equations. Okay. Now, if you look at this particular set of equations, what is clear is that these are a set of homogeneous equations because the right hand side is equal to 0. Okay, and you might recall from what you've learned in linear algebra that these kinds of homogeneous equations will have a non-trivial solution. Okay, only if the determinant of the matrix is equal to 0. Okay, so what I mean by non-trivial is that the x vector is not 0, 0. Okay, if you say the vector is 0, 0, it doesn't mean anything, right? So if you have to have a real vector, okay, a non-trivial vector, okay, the only way you can have a solution for this problem is if the determinant, okay, of this matrix A minus lambda I has to be equal to 0. Okay, so why are we doing this? Because if you take the determinant of this matrix, okay, and then equate it to 0, what you will find is that you will get a quadratic equation in sigma p. Okay, so essentially if you think about the two principal stresses as being the roots of this equation, then what you do is that when you take the determinant of this matrix, you get a quadratic equation in sigma p, and the roots are essentially sigma p1 and sigma p2. Okay, so essentially this kind of gives you, a route to actually find the solutions for the principal stresses sigma p1 and sigma p2. Okay, so I hope that this is clear to you, that you can recast the problem of finding the principal stresses and principal directions as essentially solving for the eigenvalues and the eigenvectors of the stress matrix sigma. Okay, in the next lecture, we will actually look at a specific example of how you can use this approach to find sigma p1, sigma p2, and the corresponding directions np1 and np2. Okay, I'll see you in the next class. Thank you.